Chapter 10, Section 2, Rational Numbers as Exponents. Like I indicated a little bit in the last lesson, that we're going to get rid of these radical symbols and use exponents to deal with this, which is going to open up a lot of doors for shortcuts, and we can use our exponent rules, which can simplify a lot of things for us, or allow a lot less steps to get to solutions or simplified expressions and stuff like that. And if we can, like always, good strategy, the less amount of steps that you can take to get to the answer to the question they're asking, the better it is. Less chance of error, less steps. Okay. Well, rational exponents. When defining rational exponents, we want rules for exponents to hold for them just as they do for integer exponents. For example, we want to continue to add exponents when multiplying expressions with the same base. Again, base is in this case, this one here, the base is a and the exponent is 1/2. Well then, if we took a to the 1/2 power times a to the 1/2 power, we would get an addition of those exponents. That's an exponent rule we have when you're multiplying like bases, which would be the exponent be 1/2 plus 1/2, or 1, which suggests that 1/2 means the square root of a. Because if I take the square root of a times the square root of a, I'll get a, or a to the 1 power, and so on. And then they show us, well, if I took a to the 1/3 power times a to the 1/3 power times a to the 1/3 power, you would add those exponents because the bases are alike, or the same base. So it would be 1/3 plus 1/3 plus 1/3, which adds up to 1 again, which indicates kind of, it's not really a proof, but it looks like that must be the cube root of a. Okay, and that's what they're showing us in the box here, that a to the fractional, or 1 over n, is the same as the radical to the index n, that they work the same. And usually we're going to want to work in this fractional exponent mode because we've worked with that. And that's what it says here in words. A to the 1 over n power means the nth root of a, when a is a non-negative and n can be any natural number. Now there's finally, we get a place where we use that natural number set, is that we do not use 0. The whole number set is 0, 1, 2, 3, 4, and so on. Well, natural numbers start at 1. So we have 1, 2, 3. Or we could say all positive integers. Really, it'd be another way to say natural numbers. When a is negative, this base is negative, the n can only be odd, or we end up with an issue where we have a non-real root that can happen. In other words, we don't have anything in the real number set that would give us a root to that case, unless it's odd. Remember, odd can deal with this. So thus, like if we have a to the 1/5 power, that's a 5th root of a. And if we have a to the 1/10 power, that's the 10th root of a. The denominator of the exponent is the index of the radical expression. Index is that little number here, and the radical expression is that check mark division symbol. Okay? So write equivalent expressions using radical notation. So this would be 16 to the 1/2 power would be the square root of 16, and so on. And they show that. Okay. And other way around here too. So if we have the 5th root of 7ab, we could write that as the quantity 7ab. Make sure that you take everything that's underneath that radical symbol, in this case 7ab, is all to the 1/5 power. Okay. Now positive rational expressions Again, here's some terminology. Rational means fractional. Did I say expressions? I meant exponents. I'm sorry. Positive rational exponents. Well, rational means fractional, right? Fractions are ratio, stands for fraction. Rational, the definition of a rational number is any number I can write as an integer over an integer, or a fraction using integers. So, well, here's that natural number thing again. It says for any natural numbers for m and n, in other words, and then it says n cannot be equal to 1, they're going to limit that. For any real number a for which the nth root of a exists. Okay, so if I had the square root of -3, I have an even root and a negative radicand, I got a problem. Okay. Now if this was a cube root, which is an odd root, and -3 or whatever, that would still have a value. Okay. Based on our restrictions. Could possibly be some questions about ranges coming up again, based on some of these restrictions we have on radicals, so something to think about. Well, if we have a to the m over n, this fraction with the m and n, with these restrictions on those values, right, means that we'd have the nth root of a all to the m power, or we could say the nth root of a to the m power. Okay. So the examples here, like 27 to the 2/3 power, we could say is either the cube root of 27 squared or the cube root of 27 squared. Okay. In other words, in this case, I would take the cube root of 27, which we can, which is 3, and then square 3, and you're going to get 9. In this case, I would go 27 squared, which is 729, and then take the cube root, which seems like a harder method. And we're going to talk about prime factoring and trying to avoid these situations, so we can bring out the roots if we need to more easily by doing prime factorization and so on. But we're going to get there when we go through all the review of all the power of powers and shortcuts or rules that we can use on exponents. So look, example B here is 25 to the 3/2 power, means either the square root of 25 all cubed or the square root of 25 cubed. Okay. Now I kind of like this one in this case because I can deal with smaller numbers, and I'm not going to spend much time there because there's actually even a better way than dealing with this this way. But we take the square root of 25, which is 5, and then you cube it and you get 125. Example 4, they give us the cube root of n to the 4th power, and they want us to write that in exponential notation, or with an exponent. So we take that cube root of 9 to the 4th power and we would convert that to 9 to the 4/3 exponent of that, right, or power. Okay, and so on. And they show it with the 4th root of 7xy all to the 5th power would be the quantity 7xy all to the 5/4 power. Now, negative exponents, a little bit of review here too, is that it sure doesn't mean a negative number in the sense, but negative exponents mean we're going to have a fraction occur. And to recall, it says like x to the -2 power is the same as 1 over x to the +2 power. So negative rational exponents behave similarly. We just got to make sure that we deal with this inverse situation that occurs with negatives. And that's really what it is that if I say, x, well, let's take like 2 to the 2 power is 4. Well, 2 to the -2 power is 1/4. Well, those are multiplicative inverses, or reciprocal is a more common term for there. So that negative exponent creates an inverse situation. In other words, and then if you think about multiplication of powers, if I take x to the 1 power times x to the negative 1 power, you get x to the 0 power. And here's a little more review. Anything to the 0 power is 1. 1 is the identity, and reciprocals, when multiplied, give you 1, the identity of multiplication. Okay. Well, here's negative rational exponents. They talk about that. It means 1 over it, right? So any rational number mn and any non-zero real numbers a for which a to the n exists, which covers a lot of bases here when you're thinking about fractions, like n can't be 0 because you can't divide by 0 in a you got a fraction thing. There's a whole bunch of stuff. So they're kind of covering their base there, quite a bit of bases, with saying, hey, this actually has to exist, the deal. So when we take it to a negative, then we end up with just 1 over that. So a to the negative m over n, or that fraction, is now negative. We could rewrite that as 1 over, this becomes the denominator of that fraction, and it becomes a positive exponent. And you're going to start seeing questions again ask in your homework to say, represent your answer with all positive exponents. So they're going to have, basically you're going to have to deal with the negatives by creating their inverses and then working it from there. Here's a caution again. This was usually a place where a lot of students make errors. Right here, this caution, it says negative exponents. A negative exponent does not indicate that the expression will end up negative, because a to the negative 1 power is not negative a. It is 1 over a to the positive 1 power. Okay. So you're going to write these expressions with positive exponents. So we're going to have to do some manipulation to make sure they're positive, right? Is by dealing with that negative specifically. And here's this word reciprocal. Really, it says, well, if I have 9 to the negative 1/2 power, how do I write that with a positive exponent? Well, I put 1 over 9 to the positive 1/2 power. And then they note here, a negative 9 to the negative 1/2 is a reciprocal of 9 to the 1/2 power. Okay? Since 9 to the 1/2 power is equal to square root of 9, which is equal to 3, the simplified answer would be 1/3. Okay? Notice that they are reciprocals of each other. Okay? And they talk about that again. They're saying, hey, they're putting in red here, and they're putting, hey, this reciprocal thing is important. Okay? We're actually creating reciprocals, but it's pretty important to remember what that is and what we use reciprocals for. We can use reciprocals a lot of times when we have a multiplication going on in an equation. I can multiply by the reciprocal, and that value turns to a 1, which could be very handy in solving an equation. Okay. Now in this case, this is probably the most important part here, is to recall that a over b to the negative n is the reciprocal of it again. Here we go, right? Which is b over a, and it creates that, or makes that exponent turn positive. So if I have 3r over 7s all to the negative 5/2 power, it'd be the reciprocal of this, which is 7s over 3r to the positive 5/2 power. And here's the law of exponents. And this is review, and this works with fractional or rational exponents the same as it did with integer exponents that we've gone through before. So let me read through this again, and hopefully this is just a reminder, some stuff that you should remember from before. For any real numbers a and b, any rational exponents m and n, for which a to the m power and n a to the n power and b to the n power are defined. In other words, they exist. We don't have situations that are not in the real number set, would be another way to say that. Well, a shortcut when we multiply like bases here, that's number one. The bases are the same, a and a right here. Well, when I have a to the m power, any exponent, times a to another exponent, well, I can just shortcut that by adding the exponents. And I could go through how that works again, but if that's confusing, just look it up in the book and they'll talk about laws of exponents again, and go back and they'll show examples and reasoning behind why that works. Well, division of like bases here on number 2, you subtract the exponents, okay? And then if I have a power of a power, you multiply the exponents. And also you can distribute the exponent over a multiplication. And though it's not really a proper term to call it distributive, but it does end up being this a to the mn, right? You can treat these as, this is like a 1, it would be a to the 1 times m, and b to the 1 times m, and so on. So apply these laws in these examples. So if I have 3 to the 1/5 power times 3 to the 3/5 power, notice that they're like bases, so I can just add the exponents. So I'll end up with 3 to the 4/5 power, okay? And so on. Here's a division and subtraction of the exponents. Power of power is multiplication, and then this shows what happens when I have multiple multiple variables, or a multiplication all to a power. We can deal with that, okay? And then they give us a strategy, really. This is not a rule or a law or a property or anything else. This is a strategy to work with radical expressions, which is a very good thing to look at, because we can you can do things in different orders as long as you always follow the rules, but a lot of times there's a good strategy that's going to save you a lot of steps and a lot of chances for error. So one is convert radical expressions to exponential expressions, or change the radicals to exponents, okay, with this idea using fractional exponents. It says use arithmetic and laws of exponents to simplify, okay, arithmetic, I guess would be a better way to say that. And so we're going to use this stuff here, right? Use these things, because that's going to make things a lot less complex to do whatever we're trying to do. And then convert back to radical notation as needed. And I would only do that if they ask for it in radical notation, and so on, okay? So look at this example. It says use irrational expressions to simplify. Do not use exponents that are fractions in the final answer. So in other words, they're going to make a restriction on how we can do the final answer. If I have a fractional exponent, then I have to convert it back into the radical. And usually the only time you're going to do that is when they say do that, okay? Well, a here is the 6th root of 5x all cubed under there, the quantity 5x cubed. Well, first thing is to convert it to fractional expressions, right? So we end up with 5x to the 3/6 power, which I can simplify that fraction to be 1/2. Or in other words, I end up with 5x to the 1/2 power, so is the square root of 5x. And this is really going to show you some things of what's really powerful about fractional expressions, especially when you have the 5th root of t to the 20th power. Well, that's t to the 20 over 5, which simplifies to t to the 4th. And that is the answer. I mean, there's no fractional exponent. I don't have to deal with any radical symbols. If I have something like this, it's all to the 12th power. Well, I can take this scenario and say that this ends up to be a b squared c, the quantity, all to the 12/3 power again. Simplify that fraction, you're going to end up with 4. And then a better way to show this expression is to use the law of exponents, and I can say this is multiplies against each one of these factors in here, right? Which is a is a factor, so it ends up to be a to the, it's really a to the 1 power, so a to the 1 times 4 is a to the 4. B to the 2nd times 4 is b to the 8th. C to the 1 power times 4 is c to the 4th. So this would be the proper term, proper way to show the result of those, the manipulation of this radical and exponents. Here is a square root of the cube root of x, which is, let's break it out. Let's start kind of like order of operation. Let's go into the innermost grouping in here, which is the cube root of x, which I can rewrite as x to the 1/3 power. Well, the square root of that is the 1/2 power, so it is the quantity. It's not really a quantity, it's just x to the 1/3 power to the 1/2 power. Well, our power laws of exponents say, well, I have power of a power, so you multiply those two exponents, which is 1/3 times 1/2, and you get 1/6, which is converted back to a radical as the 6th root of x. And that's a pretty short section to go through. Like I said, it should be a lot of review. It's just, instead of using integers, we're going to use rational numbers for exponents and apply the same rules.